So if you think about being able to heat a pot of water, right? Or you just leave a pot of water outside sitting on the porch or your deck or your patio or wherever you have it. If the sun comes out and it gets warmer, you know it's going to do what faster? Virginia's Michael.
I was going to see how you did yours.
Oh, what's her face? Hunt told me because she was texting with somebody or chatting with somebody at the central office, and she had me. She was a little surprised I turned this in. I said, "Why? I gave it to you." She said, "None of the rest of y'all turned these things in." I said, "Why? I gave it to me. I've turned mine in."
Well,
So,
well, Potts brought it to my attention.
okay.
She was like, "Have you not been doing crap on this?"
So I put down that I go from here to Duke Drive, and then she had me. She checked, and because my house is further away than the school, she had me put 3.1 miles back. So I put Duke Drive back to the school because it was 9 miles home and only 3 miles back to the school. It was a shorter distance home or to the school than it was to home. I only put the 3.1 miles back to the school because it was less than going home. So which one's shorter, home or school from your person's house?
So it's 4.8 there.
Okay.
Mine is, to my house is 1.8.
Okay. So from them to your house would be how far?
I don't know.
Whichever one is shorter is the one you're supposed to put down.
It's probably to my house then.
Okay. Then that's the one. Okay. So
So I need to put from their house to mine.
on the way home, yes. If you go directly from their house home, then yes.
Okay.
Yes. But the first one from here to them, you'd put the 4.8 or whatever.
Yes.
Yes. But if you go home, then there to your house.
Thank you.
Well,
All right.
no problem. All right. So we were okay with temperature. If the sun comes out, it heats it, makes it evaporate faster. If you have a small pot, it's going to take longer to evaporate. If you have a big pot and it's spread over a larger area, it's going to evaporate faster. We're okay with those two concepts. Now, once it becomes a gas, the more vapor you have, the more particles you have, the faster it will condense. Now, I asked this yesterday in third period. I didn't think about it until third period when we were talking. When do you get more condensation? Do you get more condensation on your drink cans? Like I see Selena's got a cup back there. Justice has a bottle of water. Do you get more condensation on the side in the summer or in the winter?
Summer.
Why?
Because it's hot.
It's the same answer they gave. Think about it. It's not about heat. Why you get more condensation on the side of your cans and bottles in the summer than you do winter? It's not about the temperature outside.
Because the sun's out.
What do you have more of in the summer than you have in the winter?
The sun.
Sunlight.
Humidity. Yes.
More water vapor in the air, okay? There's more condensation on the side because there's more vapor particles in the air to condense. There's a greater concentration of water, so it can condense more on the side of the can, okay? So number 2, or 3 rather, what happens to the evaporation and the amount of water in the liquid vapor system when temperature is raised, okay? So what happens to your evaporation if you heat it up? It increases, okay? It goes faster, all right? If the temperature is decreased, what happens to the amount of water? Do you get more water or less water if you decrease the temperature? More water. And the amount of vapor. What happens to the amount of vapor? You'd have less because it turns back into the water. Okay? And these two actually come from your homework that we're getting ready to go over. All right. So let's look at homework real quick and see if you have any questions on that. So I need to get Eduardo one because he was absent.
I lost it.
I'm sorry. One for you. All right. So let's do that first, and then we'll do the graph second. All right. So on question 1. Where's mine? So I got the questions. All right. So number 1, you have a liquid vapor system, just like we were talking about yesterday. And it says, what would you do to temperature to get these things to happen? If you want a higher rate of evaporation, what do? Do you, hold on, let me read the question. I might be reading it wrong. Suppose the temperature is increased. How does the final rate of each of the following compare to its initial value? Would the answer be higher, lower, or the same? So if I increase the temperature, what happens to the rate of evaporation? Does it become higher, lower, or stay the same if you increase the temperature? It's higher. What happens to the rate of condensation? is higher, because if evaporation is higher, all right? If evaporation is higher, okay, if your water evaporates more, what are you making more of? More vapor, right? If you make more vapor, what happens more? What? You condensate more, right? So if you condensate more, you're going to have a higher rate of condensation. So that's why B is higher. Okay, you made more vapor, so you condense more. All right, C, what happens to the final concentration of vapor? Does the vapor go up and increase, or does it go down? Do you have more vapor or less vapor if you increase the temperature?
More.
You got more. It's a higher vapor. All right, what happens to your amount or final number of liquid molecules? It's less, because what'd you do with the water? You turned it into what? You turned it into vapor. The only time you're going to wind up with more water is if you do what to it? If you decrease the temperature. The only way to get more water is to lower the temperature. If you increase the temperature, the water turns into what? Vapor.
I thought it was like,
You thought it was what?
like the water,
No, it's just saying in the container, if you heat the water is going to change to vapor. So anytime you increase the temperature, you increase evaporation, you increase condensation, and you increase your vapor. Okay, those three things are going to happen anytime you increase the temperature. Okay, the only thing that's going to become less is the amount of water, because it turned into vapor. You increase the rate of evaporation, so you're increasing the rate of condensation. Does that make sense to anybody besides me? All right, Abraham's nodding yes. That's a good sign, considering he thinks all the smart people are not here today. Y'all are smart too. I just need you to realize that. All right, and 34. Now, this one's asking you what you would need temperature-wise to get these to happen. So if you want a higher rate of evaporation, what would you need to do to temperature? Increase it. If you want more concentration of vapor, what would you do? I heard Xavier. What about the rest of y'all? Increase. You need to have a higher temperature to get more vapor. All right. What would you do to get more condensation? You increase it because you need more vapor. Okay. What would you do to get more liquid? You'd lower or decrease the temperature. Yes. I just needed class to not be here so I can hear Celia. I haven't heard her talk so much the whole year. Plus her mouthpiece is not here today. Okay. Questions? All right. Let's look at the graph. This is the back of the graph I gave you the other day, Eduardo. All right, so if we look at this graph, all right, the first question said, all right, at what temperature would the liquid boil at atmospheric pressure of 400? So, and I can't draw this very well, all right, but you're essentially drawing a line across here at 400, and you're looking for the temperatures. All right, it's much easier to do this on paper than it is up here, okay? But you're looking for the temperatures that go with that line. So what'd you get for number one? You got what? I heard 38. What'd you get? 35? 38? I had 36. Is everybody in that ballpark? Yeah? Okay. For number two, what'd you have for B? 69? I had 70. Our answers are not going to be exact. If you're in the range, it's fine. All right, for three, what'd you have? All right, 98, 100, I had 97. Everybody in the range. Okay, it does not have to be exact. All right, 4, 5, and 6 wants you to find how low must the atmospheric pressure be to boil at 35 degrees Celsius. So this time, taking 35 degrees Celsius, straight up. Okay, so and these are going to have a little more play in them because these ranges are much longer and much wider around the y-axis. So in 4, what'd you get? All right, you got 400. I hear 398. What'd you have back there?
Yeah, I mean, no.
What'd you write?
Nothing.
Nothing. Well, that's honest. What'd you write?
You wrote something I heard.
Nothing.
I heard it.
Leah, what'd you write? All right, I have 370 because it's not on the line, so mine's lower, and the unit is torr. All right, for 5, what'd y'all put for B? All right, 175. I had 180. What'd you have? 150. Torr. All right, for 6, what do you have here? 30. I had 50. Torr. All right, number 7, normal boiling point. What did we say normal boiling point was yesterday? How do you find normal boiling point?
Oh, the one that
Standard temperature, 1 atmosphere, right? But this one's in torr, so what's torr? So estimate 760 across the graph. And again, read down. My lines aren't very straight, which is why I keep looking at my real graph. All right, so in 7, what'd you estimate? 50. I had 52 degrees Celsius. What'd you have in 8? I had 81 degrees Celsius. What do you have in 9? 105, 110. I had 110. All right, 10 is the one everybody asked me about yesterday. All right, which liquid has the strongest intermolecular forces? The strongest intermolecular forces equal the highest boiling point. Okay, so whoever has the highest boiling point has the strongest intermolecular forces. It means you're the strongest and the stickiest. You hold together the best, and it's harder to separate your intermolecular forces. So who has the highest boiling point out of A, B, or C? That's why they have the strongest intermolecular forces. Okay? Everybody with me on the homework? Any questions on anything we've done the last 2 days? The exception of Eduardo, who is absent, the other 6 of you need a writing utensil. Okay? No, just a writing utensil. Oh, you need your reference table and a calculator.
trying to grab a new one.
Cancer's the number 1 cancer.
Oh, no, bro. You're not gonna say something.
It's not a problem here, ain't it?
You're not gonna say something serious.
Hey, Rick.
Oh.
You ready? Reference table and calculator.
You forget to say our notes.
I didn't forget to say your notes. You can't have your notes.
Why not?
Because I said so. Is there a reason y'all drink water by the gallon truck?
I'll drink bottles of water.
It's too lazy to refill bottles. Okay, so y'all just carry it by the gallon. It would seem to me to be heavy after a while.
No, it's lighter. That's how you stop wanting to carry that when it's heavy.
Okay, so it forces you to drink because it's heavy.
What do you say?
Makes complete sense.
Oh, my.
All right, everybody got their quiz paper except Eduardo. Do I remember everybody?
said this was 10 questions.
Yes, it's long back.
14.
There's how many, babe?
Well, there's 14. Doors number 10 have 4 marks. Come on now.
Stop at number 10. I ran off the wrong quiz.
Okay.
You look at the rest of the questions.
You ran off the wrong.
What 3-phase
Come on
changes are endothermic? Right.
Oh, you did
Okay,
say
hold on, just shush. Yeah, the other 10 are right.
We might as well.
Yeah, I just only want you to go do 10. Go to the other first response questions. So we'll do 10.
No extra credit if we do.
All right. Extra credit.
You don't even know the definition for confusion. I didn't get it.
So what did we get it right?
No.
Extra credit.
1 through 10. Just answer 1 through 10.
Okay.
I only said that like 4 times. How many of you are still working? Two. Still working, Justice?
Yes.
Okay. Okay.
I'm still working.
You're still working? Okay. Mm-hmm. 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 Oh, I didn't even put his name. I didn't do that. Oh, no, I didn't know who all that. Wow. See, I didn't even calculate it, I just, mhm. And it wasn't pulling mine out. I don't know, Melissa was filling mine out for me because I was lost. I just go in. And did it, and so it pulled it out for me.
Probably a lot better.
It's easier on everybody. I just told her I thought I was doing it. She's like, I'll do it for you this way. It works. I knew that she would. And then she was like, well, are you working anymore after today? I said, yeah. She said, well, they want you to go ahead and fill it out. I said, I don't know what days I'm working beyond today. I said, I won't work next Wednesday. I said, but that's all I know. I said, there'll be more. I said, that I could do after next week. I could do 2 days a week if I have to. I said, I'm praying she doesn't want me to do 2 days of the week until she takes the exam. She said, oh. I said, oh. So yeah, I'm not done. Sorry. Here? Oh, okay. Gotcha.
Ms. Walker,
Yeah.
for number 3, is it, Ramsey or other person?
It is entirely possible, yes. Does that mean you're done, still working? Done? What about you, Chief? Done? Abraham, what about you?
Just go back.
You got to change it, work it?
Yeah, like, I wasn't sure, I just guess I'm just reading.
I'm like, 10 minutes, come on! We've been working 25 minutes on 10 questions.
All right, but you could get through class faster because it's less people. Means less questions.
Laura's gonna have all the notes taken from yesterday, all the videos I was.
That's what we were trying to help them with. That's what we were doing.
Ah,
We got you.
so like. All right, so let's start by phase diagrams.
Let's not.
Yes, let's.
Ms. Walker.
What?
How did you do local on that? And there was
You might as well grade the quizzes and you can go.
I can't tell you because people will watch the video.
You might as well cut off the video.
you tell me if I got it right.
Just pause the video.
I got
Go,
that
this-
wrong.
There's no pause.
Really?
Yeah,
There you go, this is,
Watch-
oh, this is the answer. Got it. And then go to the.
There is no way to do that.
I got them both wrong.
Xavier got it right, Jonathan got it right, Selena got it right.
Oh, what was
Somebody
that?
with blue ink got no name on paper.
Oh, that's me. I got it.
I got it wrong.
You got A right.
Hey, what was that one on
So what is it?
About 9.
with sublimation?
I
Is that
just checked the
sublimation?
gas scales.
Sublimation changes from a what to a what?
I don't know.
Solid to gas.
I think I got it right.
I got that wrong.
No, I didn't. I
100%
did get
got
it
that
wrong. Wait, yes,
And
I
I
did
don't
get it
change
right.
from a solid
I
to
knew it was
gas.
Yeah, I 100%.
So it jumps from
Yeah, you picked freezing.
I know.
I got it
I
wrong.
realize that now.
For which one?
Yeah, I think I need.
You gotta know sublimation changes from what state to what state.
yeah, I knew that one because I knew it was
Yes.
the,
I got it wrong.
One that goes from S to G. Yes, you did not pick S to G.
I knew it was the last one because
Because
I knew it skipped the spot.
It was.
You know, it's like, oh, yes. I knew it skipped something. Shut up.
I mean, those are questions that I would have thought would have been easy. Okay, those were what I would have called memorization kind of questions. A requires you to think a little. But
You
7
require
did
us
not-
to remember a lot.
7 did not require you to think.
You require us to remember.
That was, did you know the definition?
Yesterday I would have
Let's talk about it.
All right, phase diagrams. Okay, phase diagrams are just graphs of temperature versus pressure that show all the states where a material can exist. Now, we're going to have to be able to find certain things on this graph. Now, I'm drawing it small here. I'll draw it bigger in a second. Pressure is always on X. Sorry, Y. Temperature is always on X. Now.
Wait.
Pressure is on Y. Temperature is on X.
Graphs of temperature versus pressure.
It's always going to be temperature versus pressure. That shows all the states, left my S off, where a material can exist. So, the nice thing about this graph is it is always in the shape of a Y of some form. The Y may vary slightly, but it will always be a Y graph. Okay? And in that Y graph will be all 3 states of matter. And there are several points we have to learn to find on this graph. Now, in this Y graph, the solid is always over here. The liquid is always in the middle of the Y, and the gas is always below the Y. That never changes. It does not matter how they shift the Y, it always looks that way. Okay? Liquid is in the V of the Y, solid is on the left, and gas is on the right. Okay? Now give Xavier a minute to get that. I'm giving you a moment while I go put these 2 tests in the back.
So, okay, open to window now. Okay, so was hey.
All right, you got it? So when we look at the graph, there's 3 points we got to be able to find. The easiest one is the triple point. Okay? The triple point is the point a solid, a liquid, and a gas all exist at equilibrium. the point that the solid, the liquid, and the gas all exist at equilibrium. So we want to be able to find this on the y graph. It is the point of intersection on the y. Okay, it's nice and easy to find. It's the point of intersection on the y. Is everybody caught up? So can I go back? Okay, so if I go back here, all right, where does it intersect? Right there, in the middle. Okay, right there. That is the triple point. Okay, so if I need the triple point temperature, how do I find the triple point temperature? I do what, Celia? I just go down. Okay, and if I want the triple point pressure, I do what?
Go straight.
I just go straight over to the left. Okay, now that's the one everybody always remembers how to find on the quiz or the test. That's the easy one. It's the other two, and people go, dang, I forgot. Okay? So we got to go do the critical point, and then we got to do the normal boiling point and the normal freezing point. Okay? Does everybody have what they need? You with me, Xavier? Wake up. All right, so the critical point. Now, I do not know why scientists did this, but you see how the triple point had one definition? The critical point has two definitions. All right, we separate this into the critical temperature and the critical pressure. Okay, the critical temperature is the temperature above which a liquid can no longer exist. Okay? Once you pass that temperature, no more liquids. Everything after that will be what state? What state comes after the liquid?
Yes.
That's right. All right. All right. The critical pressure is defined as the lowest pressure at which the substance can exist at the critical temperature. Now, they're sort of opposite definitions of each other, but they mean the same thing. Once you get to this temperature and this pressure, everything after this temperature and pressure is going to be a what? Everything after this temperature and pressure is going to be a what? It's going to be a gas. Okay? So, if you're before this temperature and pressure, you're a liquid. After this temperature and pressure, you're a gas. And why there are two definitions to say the same thing, I don't have a clue.
You wrote two does.
Oh, I did? Make one go away. All right, so how are we going to find this? It is the end of the liquid vapor line. Okay? Sometimes it has a dot. Sometimes it's just the end. Okay? If there's no dot, it's just the end of the line. Okay? So you won't know until you see the graph. Some graphs are real nice and they show you the dot. And sometimes graphs just have a line and the line just stops. Okay? So if the line stops, just use the end of the line. A lot of times though, they'll draw a dot. But it's always the end of the liquid vapor line. Because at the end of the line, it stops being a liquid and it changes to a what? A vapor. Okay? So, everybody good so far? Can I go back? You said no? I'm back. Okay, so if I go back to my graph, so the last one we'll put on this graph, and I'll draw a new one for the last 2 points. Okay, so if I go to my liquid vapor line, okay, I have no dot there, right? So right here at the end, all right, that will be the critical point. Okay, so that's the critical point. So if that's the critical point, where do I go to get the temperature again? Straight down. And if I want the critical pressure, I go where? Straight left. Okay? Everybody okay on how to do that? Down for temperature, cross for pressure. So we feel okay about that. All right. Now, the last 2 points go with last night's homework. All right. So the last 2 points are normal, freezing point. What's the opposite of freezing point? Okay, melting. You had it right the first time. All right. And we're going to abbreviate this NFP and NMP. Because I don't know about y'all, but I'm going to get tired of writing out normal melting point, normal boiling point. So we want to use abbreviations so we don't have to keep writing that out. Okay? And we're going to do normal boiling point. Okay? Now, we don't really have a definition we have to learn here. So what did we do last night in the homework and yesterday when we were talking about finding the normal boiling point? What do we have to do? Does anybody remember?
Temperature or
Not the temperature. The STP. Okay, very good. So we're going to draw a line at standard pressure. Now, this one will be the intersection at the solid liquid line. Now, the normal boiling point or NBP will be the intersection at the liquid vapor line. And we're going to draw this after you catch up with how to find it.
That's what they said.
Where at?
Solid liquid.
Mm-hmm. Solid liquid.
Spotlight. Let's drop this fast one. Did I talk a little Friday?
Ah, everybody caught up? All right, Avery's nodding yes. All right, so if we make just another graph that doesn't have a bunch of clutter on it, okay, temperature, pressure, I'll make it look like that. All right, what do you want to label our pressure? Torr, okay, we can do torr. All right, what's standard pressure in torr? 760. All right, so let's say that I make my 760 about here on our graph, okay? So again, I'm going to draw a line in across my graph. All right, my graph's getting a little crooked here. You know, it's hard to draw dots on this board. It's easier on the other board. Okay, so we draw a line in. Okay, so that dotted line is the line that you draw in. Not very straight. Probably be easier on paper. Now, this intersection right here, okay, because that's the solid, that's the liquid, that's the vapor, correct? All right, so this intersection right here would be the what? The intersection between the solid and the liquid would be the what? That's right. So that's the normal freezing point, and that's the normal melting point. Okay? Because solids to liquids do what? What happens between solid and liquids? They melt, and I heard somebody else say they freeze. That's what happens. That's why it's the NFP and the NMP. All right, and if I keep reading across, what's this intersection? All right, that's the normal boiling point, because what happens when a liquid changes to a vapor? You can boil. Okay? Questions about any of those points? Think you could try to answer some questions about it now that we've labeled the points? Okay, let's try it. Here. Jonathan. All right. So read the questions and see what you can do. Okay. Again, it's a Y graph. The Y looks slightly different. But answer them real quick. I'm liking this whole grade 6 quizzes today. No justice if you haven't got the 7 on.
Trash. That's what it is. What's good? You said, that's what it is.
All right, we done? Yes? All right, let me pull up the phase diagram.
What I make?
Pay attention. The names. Usually don't pay attention to the names, so I put them in the computer, which I didn't do. I only paid attention to Justice because he never asked me about number 7. 8. See if this is it or the other one. I can't remember which one it is. Phase diagram 1 or phase diagram. Yes, I guessed right. All right, so find the questions. All right, so question 1. Which section represents the solid phase? The liquid phase.
C.
And the gas phase. Excellent. What represents the triple point? D. And the critical point?
E.
And what is the substance's normal melting point? 60. All right, what is the substance's normal form point? 100. Did you put degrees Celsius on the answers in number 6 and 7?
Yes.
If you did not, I would have taken off 1 point on those. All right, above what temperature is it impossible to liquefy this substance no matter what the pressure? 110 degrees Celsius, right? At what temperature and pressure do all 3 phases coexist? That is very good.
Wait,
We needed both. The question asks you for temperature and pressure. So 45 degrees Celsius and 0.5 atmospheres. You needed both answers to ask you both. All right, is the density of the solid greater than or less than the density of the liquid? Greater than. What's the only thing we've talked about all semester that's less than? Anybody know?
Wait, I already. What did you say?
And number 10 is the density of a solid greater than or less than the density of a liquid? Greater than. We've only talked about one thing where the solid is less than the density of a liquid. All semester. Anybody know what it is?
Ice.
That's correct. Water. The solid ice floats in the liquid water. It's the only thing we've done. All right, when an increase in pressure causes the substance to freeze or melt. Look at your graph. All right? What's happening? All right, pressure is increasing. What's the solid doing? Is the solid section getting bigger or is the solid section getting smaller as pressure increases? The solid section is getting bigger, right? So if the solid section is getting bigger as pressure goes up, what is it doing? If the solid section is increasing, is it freezing or is it melting?
Melted.
All right, I got half of you yelling freezing, half of y'all yelling melting. If the solid section's getting bigger and you're making a solid, this is why y'all got 7 wrong. Y'all don't know your phase changes. If the solid is getting bigger and you're making a solid, if you change into a solid, are you freezing or are you melting?
Melted.
You're freezing. You melt when you turn into a liquid. Right? That's why half of you didn't know what a sublimation was on the quiz.
Did I get that one right?
I don't remember. I'd have to go back and look at your paper. All right. Now, that's not what I meant to do. Come on, thing open so I can close you.
And then you stop working. This is what we all.
What?
What?
What's making you mad?
Just,
Oh, us Justice making you mad.
he did something very impolite.
You know, I teach in a high school. I hear it impolite and see it every day. I had a fight almost break out in fourth period yesterday because somebody said bless you and somebody didn't say thank you.
You really, like, was it really about to be a fight? So
No, but the escalating, arguing back and forth about you shut up, and get out of my business afterwards, almost did.
who was it?
Never mind. All because somebody didn't say thank you after somebody said bless you afterwards.
The police.
It was one of them. Now, kinetics. We're going to talk about kinetics and collision theory and potential energy diagrams next. Okay? Now, this will roll over into Monday because we will not have time to finish this whole topic today.
You got a
Okay?
quiz on Monday?
Huh?
You got a quiz on Monday?
No, but we will work on this after our lab on Monday because the lab will not take the whole class period Monday. All right?
So
Now,
you gotta write down the.
have we written our procedure and data tables?
No.
If we have not, remember what I told you. You do not get to participate. Even if you write it while I'm talking, I will stop you and tell you you cannot do what? Participate. And I have no afternoons next week to make it up. It will roll into the next week because the one day I had for makeup work is now a rally day for us to go to Raleigh. So I have no afternoons next week for makeup work. I mean, the only thing I have is if you want to come, like if you want to make up today's quiz, Eduardo, and you want to do it Monday after school, I can stay long enough to do that. But that's really all I've
What
got.
about last-
Okay? Huh?
Are you going to Raleigh?
No, I'm not. I can't take the chance that I won't be back Wednesday evening.
What about last week?
Huh?
What about last week's quiz?
Last week's quiz, if it's really quick Monday afternoon and you stayed right after school, yes, I could probably do that. But it has to be Monday. I can't do it Tuesday or Thursday.
What was the first one?
What about when we come in the morning?
Today I was still in the annex building until 8:25.
Oh.
Okay, I was here by 7:55, but you know sometimes I come in the annex building and I just stand and socialize, and I didn't get down to my room to 8:25. I have a terrible habit of that with first period planning. Somebody stops me, I stop to talk, and it's game over. All right, so kinetics. Kinetics is all about the rate or speed of a reaction. Okay, the biggest thing I want to point out about kinetics is it's not if a reaction will occur. Okay, that's not what we're talking about. We're not talking about if it will occur. We're talking about
When it will.
how fast. Okay, just simply about how fast. Kinetics is about speed and how fast, not if. All right, we're going to talk about if it will occur. Probably Thursday. I was going to say Wednesday, but I forgot we weren't here. Thursday. Yes. Okay. So, in order to have a conversation about how fast something will occur, we have to talk about collision theory. Okay. So, we'll talk about that in a little bit. There are 5 factors that affect rate. Okay? And we're going to talk about how it affects collision theory and all that in a little bit if we have time today. Okay? But essentially, when I get there, we're going to talk about the fact that we want collisions to occur. The more collisions you have, the more successful a reaction can be. So you want to provide opportunities for molecules to collide. So how can you do that? How can you give molecules more opportunities to collide? How can you encourage collisions? How can you do that?
Speed.
How can we speed them up? Increase their temperature. Okay? If we increase the temperature, molecules move faster. There will be more opportunities for collisions. Okay? because reactions and being successful are all about the collisions and having successful collisions. Most collisions between molecules do not result in successful collisions. The best example I can give you is giving you an electrical cord and blindfolding you and telling you there's the outlet on the wall and telling you now go plug it in. Okay? Can you get the outlet and the cord lined up blindfolded?
Yeah.
Eventually, you can. But you're going to have to do it by feel, and you'll eventually get there. But can you reach out blindly the first time and get the prongs to go in the outlet, in the
I'm
hole?
pretty lucky.
You're pretty lucky. Well, sometimes molecules hit the right energy and the right orientation, which are two things we'll talk about, and they get it the first time out. It is incredibly rare. Okay? Most times the molecules bump up against each other. They don't have enough energy. They're not oriented correctly, and they just bounce off and go their own way. Okay? Same thing. If I gave Celia a blindfold and she couldn't see, and I gave her an electrical outlet and a cord and said, plug it in. Odds are good. Are you going to hit it the first time? No, I'm not in. I'm going to be up here probably for a half hour trying to get that stupid cord in, get mad, throw it down. Be like, I can't plug it in that way. I'm going to do something else. Okay?
Play that game.
Let's not. I don't want you to be electrocuted either. All right, so what is something else we can do to increase our chances of collisions and have successful reactions besides just increasing the temperature? Make sure I haven't forgot anything.
Wait, what did you say?
What else can we do to increase our chances of successful collisions besides just increasing the temperature?
Making it small.
What do you mean by make it smaller?
Area.
What?
Smaller area. Surface area.
There we go. All right. So increase the surface area. All right. For example, let's say, let's use a word you know. Granulated versus cubed sugar. Clearly Xavier's not been shopping.
Yeah, I never bought cube sugar.
Me either. I don't need it. I just know we can.
It's like tea party thing.
Exactly. Now, if I was one of those people who serve tea, I'd buy cube sugar because I can't stand the mess. All right, so my children sometimes in the summer are like, Mom, let's make some Kool-Aid. I'm like, oh dear God. Because my son is messy Martin. There's Kool-Aid powder on my counter. There's sugar on my counter. What happens to sugar if you don't clean it up? Anybody know?
Ants.
Ants and sticky. Okay? So, if you look at these two, which one has more surface area? The little cube sugar has surface area around each individual grain. And this is by no means all the sugar. I just got tired of drawing dots. Okay? Whereas this cube sugar, the water has to attack the outside on each surface and break it down, and then it keeps attacking from the outside. But on the granulated sugar, this is already broke down into individual specks. It doesn't have to work near as hard to dissolve that. So anytime you have an increased surface area, it's much easier to dissolve and react. All right? Give me something else.
Less pressure.
What?
Less pressure.
That would only be good for gases, so let's not add that one because it doesn't affect solids or liquids. I want it to affect all three of them. One's a biology word that I'm looking for, and one is something we talked about yesterday.
What's the bio?
You would have talked about it in biology to speed up a reaction, make it go faster. How could we get more collisions? Everybody in here has had biology, so y'all should be able to tell me. There you go. Add a catalyst. A catalyst, its sole function is to speed up a reaction. It does not participate in any other way. Okay? It does not participate in any other way. All it does is make the collisions go faster. Speeds it up. All right? The other word I'm looking for was one we talked about yesterday. Anybody got an idea? Because the fifth one you're going to need me for. You're not going to think about this even though you know it. Start with a C. Concentration. All right, so number 4 is increase concentration. If there are more particles, there will be more collisions. Remember, concentration is about particles. That's the definition of concentration. So, if we have more particles, there will be more collisions. It's sort of like going up the main hall right now at 11:30. Are there going to be a lot of people in the hall right now? No, there are not going to be many collisions because there's not a bunch of people there. What if I make you go to 11:42? Will you have many collisions?
Yeah.
I dare say I can't send Eduardo up the main hall without bumping into somebody, can I? No. Okay? You're not all that hefty. All right? You're an average sized guy, high school age. If I send you up the main hall, can you go up the hall without bumping into a soul? No. Okay? Really? Without trying. Okay. Somebody's going to bump into you just because there's some.
If people go around me.
Okay. Number 5 is the nature of reactants. Now, nature of reactants is just sort of a generic name that I give it because of things we already know. What things on the periodic table could you tell me is just naturally going to react faster? Give me something you've learned this semester is going to react faster. What? Why is chlorine going to react faster?
It's a halogen now.
It's a halogen, so where is it?
Group 7.
Group who?
Group 17.
There you go. Now, that mistake would cost you on the exam because group 17 would have group 7 in the question, hoping you'd remember the electrons and not the group numbers. Don't make that mistake. All right, group 17 has 7 electrons. So we know that's very reactive. All right, give me somebody else who you know would be pretty reactive. Group 1. Okay? Group 1 has 1 electron. Again, that would be very reactive. So what can you tell me about their speeds? They're going to be fast. Okay? These are going to be fast. Now, who would you put in the slow category? All right. The middle is going to be slow. Now, you keep telling me about group 18. Where's group 18 going to fall in this? They're going to be what, Justice? That's right. Group 18 has 8 electrons. They're going to be in the not react. Okay? They're not going to do anything. They're not going to react at all. They're just going to sit there and do nothing. Now, the slow, all right, the middle of the table in the D block, they're in your slow category. So your D block's going to be in that slow section. But group 18, they're not going to react at all. So if you're looking for slow, they're going to be non-existent. You're going to be waiting years and probably still get nothing. Unless you manage to get lucky and pick some elements like fluorine Fluorine might react with the bottom three of the noble gases. But odds are good, it's not going to do a thing. Okay? Now, does everybody have what they need? So, I alluded to what we need for these collisions to occur, right? So, what are the requirements for a successful collision? Okay, what do we need for a collision to be successful?
Okay, so each other.
Okay, number one, sufficient energy. When they collide. So, when Xavier said they got to bump into each other, they do. They have to collide. But when they collide, they have to have sufficient energy. So, this energy is going to have a name. And you're going to hear more about this than you ever wanted to know on Monday. It's called activation energy. And we're going to have to learn how to graph it. It's our last graph. It's called activation energy. And the second thing that you have to have aside from sufficient energy is you have to have, what was I talking about with that outlet? You have to have proper orientation. So not only do the molecules, when they come flying at one another in the container, have to have this minimum or sufficient energy, they also have to have the correct orientation. So, have any of you ever gone to plug in an outlet, maybe a lamp or another appliance, and you go to plug it in and it won't go? What do you have to do? You might have to press it harder, but most of the time, what's wrong with it? You got to turn it around, okay? It's got a wide end, which is the neutral slot, and the other one's the hot slot. So you have to flip it and turn it the other way. It's not oriented properly. Some of them are three-pronged. One of them's a ground, and the other two are the neutral and the hot slot, and you have to orient them correctly to fit in the holes, okay? Molecules work the same way. They have to be oriented correctly. If you have a two-pronged plug and it won't go in the outlet, you have to flip it so it will go in. Molecules work the same way. They have to be lined up correctly. If they're not lined up correctly, will they go in the holes? No. Okay? So, what are we going to do with this stuff on Monday? Any ideas? No. We're going to draw potential energy diagrams. Okay? Now, I don't have time to draw an entire potential energy diagram, so I'm going to define one word, and then I'm at after 11:35, so I'll probably quit with y'all since there's only 7 of us. All right, the one thing we're going to have to put on the diagram is activation energy. Now, activation energy I think I spelled it wrong. Activation energy. That should be right. All right. Because it's an energy, its symbol is E. And we give it a sub A to remind everybody that it's activation. Activation energy. We don't use a capital A for energy. We use an E because that's the symbol we always use for energy. Now, what? Why did I put what backwards? Oh, because the capital E is always energy. Like when we abbreviate kinetic energy, we use KE, potential energy is PE. So it's always written that way. Why we didn't use like activation energy this way, I have no idea. But they use big E with a little a for activation energy. All right, this is the minimum energy needed to start a reaction. All right, it's the minimum energy needed to start a reaction. Now, think about it this way. Activation energy also applies to y'all. Some reactions do not require a lot of energy to get started. They're going to have very small humps on this graph on Monday or Tuesday because they don't require a lot of energy to get going. Okay? Some activation energy require a lot of energy. They're hard to get the reactions going. So think about yourselves in the morning. Any of y'all easy to get out of bed? Early birds?
Yeah.
Easy starters? If you are, okay? Then your activation energy hump would be very small because it's easy to get going, okay? My personal children are not that way. It's hard to get them out of bed. It's a fight, which is why I'm usually here at 8 o'clock. I used to get to school every day at 7:20 when it was only me because I'm an easy person to get out of bed, okay? So my hump is small. My kids is gigantic. So Jackie is always late for first period. She's probably got a huge energy hump. So when we talk about reactions next week, those that are slow to start have a big hump. Those that are easy to start have a small hump. Okay? What's your homework for the weekend?
Right, procedures.
Abraham, I don't know why you put yourself in the slow category, because you are so not. Okay? You know what he told me at the start of class?